Okay, so let us recall what we have did in the previous lecture. So in the previous lecture, we have discussed about the Bessel's equation. We know that the Bessel's equation is represent, or it can be written as x square y double dash plus x y dash plus x square minus p square y equal to 0, where this value of p is greater than or equal to 0. This is known as the Bessel's equation. And we have solved this Bessel's equation using the Fubini's method. And we got the solution is a0 x raised to p summation n running from 0 to infinity minus 1 raised to n upon 2 power 2 raised to n into n factorial p plus 1 up to p plus n into x power 2n. And to get the Bessel's function, we also define the Bessel's function. The Bessel's function is by picking this value of a0 as 2 raised to p into p factorial. We'll define the Bessel's function, and it is denoted by jp of x, which is summation n running from 0 to infinity minus 1 raised to n upon n factorial into p plus n factorial into x by 2 raised to 2n plus p. So this is the expression of the Jacobian or Bessel's function. Then the question is, to the value of p is greater than or equal to 0. That means here p plus n factorial is there. If p is an integer, then and only then there is a existence of this expression. So now the question is to generalize this p plus n factorial in terms of gamma function, or in when we can generalize factorial in general for any real number n. So for that, we have defined the gamma function also in the previous lecture. So the gamma function, we know it is denoted by gamma n, and which is integration from 0 to infinity e raised to minus x raised to n minus 1 dx. And with the help of this gamma function, we already discussed this properties of gamma function, that is n plus 1, and n is a positive real number that we have taken. For n plus 1, gamma n plus 1, we have proved that it is n into gamma n. Secondly, we have proved that a gamma 1 by 2 is the square root of pi. These are the properties of gamma function we have discussed. Also, we have discussed that gamma n plus 1 is n factorial if n is an positive integer or 0. So if it is 0, if it is positive integer, then it will be n factorial that we can have. So these are the properties of gamma function we have derived in the previous lecture. Now in this lecture, we'll define for Jacobian function or this Bessel's function for negative, or this p plus n factorial is our objective. So for that, we will define this gamma function for negative values also. This gamma function is defined for positive value. Now our objective is to define this gamma function for negative value also. So now we want to define. So now we want to define a gamma function for negative real numbers. So if this p is between minus 1 and 0, then this will implies if I add 1 to this inequality, we'll have 0 is less than p plus 1 is less than 1. Then we define gamma p as gamma p is equal to gamma p plus 1 upon p, because in that case the p will be defined for negative value, which is between minus 1 to 0, in between minus 1 to 0. And what is gamma and how we have defined this? Because of we have this gamma p plus 1 is p into gamma p. This is one of the properties there. So using that property, we are able to define this. Now, if this p is between minus 2 and 0, then the idea is to add 2 from this one. Then if I add 2 here, then this will be between 0 to 2. Then we define, in this case we define gamma p will be gamma p plus 2 upon p into gamma p plus 1. Again by the same formula, gamma p plus 2 will be p plus 1 into gamma p plus 1, and gamma p plus 1 is p plus 1 into p into gamma p is there. So the gamma p I want, I can define like this. And if you go further in the same manner, in general, for any, if your n, your p value is between 0 to this, or I may say that it is between minus 1 plus, it is between this two, for any n belongs to n. And if I add p n here, then it is between 0 and 1. P plus n is between 0 and 1. So in this case, we can define gamma p will be gamma p plus n upon p into p plus 1 up to p plus n minus 1. So this is the definition for if p is a negative value between minus n to minus n plus 1. Also we can note here that if limit of p tends to 0, gamma p as per the definition, p tends to 0, gamma p plus 1 upon p, which we have defined earlier into this gamma p plus 1 upon p, gamma p equal to, and this will give you p tends to 0, the denominator will be 0, so this is infinity, either plus infinity or minus infinity, we don't know. And the same happen for all negative integer also. That means for this one also we have the same thing. In general, for any value is between this minus n to n plus 1. So in any intervals, if I take the limit here, this quantity will be 0. Limit of this as p tends to infinity, this quantity will be infinitive. So that's why for any integer we have this. So for n belongs to n, limit of p tends to minus n, gamma p will be plus or minus infinity. This is the things we got. So the extended definition of this gamma function is defined like this. Gamma p will be having the value 0 to infinity e power minus x power p minus 1 dx if p is greater than 0. If the value of p is greater than 0, this is the value. If the value of p is negative and it is in between this two consecutive number for some n belongs to n, then the value of this one as per we have defined it is gamma p plus n upon p into p plus 1, p plus 2 up to p plus n minus 1. So if the gamma is negative value, we have defined like this. And if p minus p is belongs to n union 0, that means p is 0 or negative integer if it is there. See, this is between, it is not an integer, yeah, it is a value of p is between minus n to n plus 1. So it is any real number is between these two. If it is an integer, that what does it mean is minus p is belongs to this. That means p is a negative integer or it will be 0. Then we have defined it as infinity, or I can say it is not defined. So in that value, it will be not defined. Now there are interesting properties of this gamma function. You can say that whether it is a continuous or not, all sort of things you can discuss. But we are not interested to do that. A property of gamma function. It is lots of literature is available on this gamma function. You can just see and explore some more property of this gamma function. But here our objective is to write down that Jacobian function, so that Bessel's function into this form for negative values of gamma function. So now from this, we can define p factorial. If p is an negative number, then we can define as this. If p is not a negative integer, then we can able to do that. Okay, for both this value. So that we can write. So now we define p factorial using above extended definition of gamma function, that is p factorial is equal to gamma p plus 1 for p is not equal to minus 1, minus 2, minus 3 and so on. If p is not equal to this, we can able to write down this. So now we recall that what is the Jacobian, or sorry, that what is this Bessel's function? The Bessel's function was defined as 0 to infinity, minus 1 is to n factorial into p plus n factorial into x by 2 power 2n plus p. But we should note this p factorial is gamma p plus 1. So, but we note that 1 upon p factorial now, we can write down this is as 1 upon gamma p plus 1 if p is not equal to -1, -2 up to so on, and 0 if it is equal to -1, -2 up to so on, because in that case it is infinitive. P factorial is infinitive if it is a negative integer. So 1 upon infinity will become 0. So 1 upon p factorial is 0 in that case. So now we can able to define this for all p belongs to R and for all n belongs to a natural number. So now what we can write is 1 upon p plus n factorial is defined for all p belongs to R and for all n belongs to n union singleton 0. So now this Bessel's function is defined for all values of p which are greater than or less than whatever the value you choose. This Jacobian or this Bessel's function is there. Now our next interest is to see that what are the properties of this Bessel's function. So with regards to that, we have the first result. It says that if p equal to m is a positive integer or 0, then prove that this jm x and j minus mx are linearly dependent. Linearly dependent means one of them is a linear combination of the other. So that means jm of x is some c1 times jm minus 1 of x. So this is the expression that we require to prove they are linearly dependent. So ultimately this statement is also can be written as prove that jm jm of minus m x is equal to minus 1 raised to m jm of x for every m belongs to n union singleton 0. So another way is to looking at, or another way is to writing this expression into this form. So let us try to prove this. The Bessel's function of the first kind is, we know that it is jp of x will be summation n running from 0 to infinity minus 1 raised to n upon n factorial into p plus n factorial x by 2 power 2n plus p is there. Now let p equal to minus m, where m is an integer, sorry, positive integer, and or 0. Then this jm minus mx can be written as summation n running from 0 to infinity minus 1 raised to n upon n factorial into minus m plus n factorial x by 2, 2n minus m. Now we have to look at in what is this situation, that is if minus m is less than minus n plus n is less than 0, that will implies n is less than capital M. But this will gives you, that means the value of n is always less than m, that will gives you n will be 0, 1 up to m minus 1. So thus, in fact, this is if and only if I can say. Thus, for n equal to 0, 1, 2 up to m minus 1, m minus m plus n is a negative. So, as per the definition of this gamma function, which we have derived here, 1 upon p factorial, if it is a negative integer, then 1 upon p factorial will become 0. So, in that case, if this is the negative, that means 1 upon minus m plus p n factorial will be negative. So, and m is an integer, n is also integer because n is running from 0 to infinity. So, hence what we can say, this is negative. So, in that case, this is 1 upon m plus minus m plus n factorial will be 0 for n equal to 0, 1, 2 up to m minus 1. This is the quantity you will have. So, hence this Bessel's function for minus m will now start with, because first n value, m minus 1 value will become 0 to m minus 1, it is all of them are 0. So now this n is running from m to infinity, minus 1 raised to n upon n factorial into minus m plus n factorial into x by 2 power 2n minus m. Now we'll replace this, I will change this index, I want that it has to be start with 0. So for replacing this index, that means n replaced by n plus m. So replacing n by n plus m, we get Jm of x Jm minus m of x will be summation n running from 0 to infinity. Instead of n, we have to replace n plus m. So here it is minus 1 raised to n is there. So it is n plus m upon n plus m factorial, because it is m plus n factorial. Now this is minus m plus n plus m factorial x by 2 power 2 m plus n minus m. So this is minus 1 raised to m is common out from this summation n running from 0 to infinity, minus 1 raised to n upon this quantity will gives you n factorial. So I am writing that is first, and this is m plus n factorial. This will be x by 2 power 2n plus m, because 2m minus m is there, so that will be m. And what is this factor? What is this quantity? It is minus 1 raised to m into Jm of x. So hence, thus, what we have is J of minus mx is minus 1 raised to m Jm of x. That means we can say that this J minus m, that is this basis function is a constant multiple of this one. So therefore, this both the things are linearly dependent. So I can write J of minus mx is a constant multiple of Jm of x. So J minus mx and Jm of x are linearly dependent. So that completes that these two functions are linearly dependent. And I required this is to discuss the next topic, that is general solution of the Bessel's equation. So that we will discuss also general solution of Bessel's equation.